So we've learned how to test for a single mean when the population standard deviation is known. But what about the more common case where the population standard deviation is unknown? What would we do? Well, if the population standard deviation is unknown, first off, we can't use z equals x bar minus mu over sigma over square root of n because we don't know what sigma is. So in place of z, we'll do the analysis in the exact same way, but in place of z, we're going to use the t term for our test statistics. So for our test statistic, we'll use the t term. And the t term is x minus mu over s, which is the standard deviation of the sample, divided by square root of n. And here we have degrees of freedom that we need to keep track of, which will be n minus 1. So you go to the t-table for your level of significance, and you scroll down and you go across the row that is equal to your degrees of freedom, which is n, the sample size, minus 1. So let's list what these terms are. So this is the sample standard deviation. We should know this. This is all review material, actually. This is the sample size. This is your sample mean. And this is your population mean. All this information needs to be given in the problem statement. So let's just jump right into an example. Okay, so here's our problem statement. A medical investigation reveals that a particular hospital has 16.3 infections per week. To check this, we randomly sample 10 weeks and get an average of 17.7 infections per week, with a sample standard deviation of 1.8. Should we, based on these results, reject the medical investigation claims? Let's use a level of significance of alpha equals 0.05. All right, well, let's use the step approach that I outlined to solve this. So the methodology is the same, but for our test statistic, instead of the z test statistic, we're going to use the t-test on this because we don't know what the population standard deviation is here. And we also have a small sample set. So to begin with, let's go and figure out what our null hypothesis is and what our alternate hypothesis is. Well, we need to come up here and we need to pick these terms out of our relationship. And this is our population mean. So mu equals 16.3. And this is our sample, and it's from this that we're going to make our claim. And we want to try to see if this is something we want to adhere to or if we want to reject this. So what we're really asking is, does the mean not equal 16.3? And we end up with 17.3. Oops. This does not equal 16.3. So for some other pertinent values, we could see here that x bar is for our sample test, 17. So from our sample, we get this information. X bar is 17.7, N equals 10. We did 10. And our sigma, it's not sigma actually, sigma is the population, standard deviation, it's S. Our S is, for our sample, 1.8. So we can use this information now. So what we're looking at here is a two-tailed test. We handle this in the exact same way we handled the previous examples where we knew the standard deviation, except now we're going to use a T for our test statistics. So calculate our test stat. So that's T. T of, it's going to be alpha over 2. Actually, it's going to be depending how you want to look at it. But we have X bar minus mu over S over square root of N equals 17.7 minus 16.3 over 1.8 over square root of 10. Okay, so now we've got to figure out our critical region. So this is a two-tailed test, like I said. We're going to have a t-value here and a t-value here as a boundary to our critical region. So if alpha equals 0.05, then each of these is going to be like an alpha over 2. So alpha over 2, half of that is 0.025. So we need to find the value associated with that. So we need to get t of 0.025. So for the degrees of freedom of 10 minus 1 equals 9, this will then require us to go to the tables. And this equals, let's go ahead and look at the table. So I can go to our tables here. And this is our t-table. And again, we said the area here was 0.025. Now this table only has one side, so this area is 0.025, so t is 0.25. So we're going to look at this, and then 9 here. We're going to come into here. So 2.262 is our value for t. So let's go back. 2.262. So that means this is 2.262, and this is minus 2.262. So let's compare then what our test value is, 2.462. It doesn't fall over here, it falls over here. I'm going to erase this alpha over 2. Put it over here. Alpha over 2. And had a zooming error there. I fixed it. So now we see that our t value is over here in the critical region. So what does that mean? So that means that we are going to reject our null hypothesis. because our test stat ended up in our critical region. So we'll make the claim there is convincing evidence at alpha equals 0.05. You always want to mention your level of significance for your statement here. There's convincing evidence that alpha equals 0.05 to conclude that the number of infections per week does not equal 16.3. And that's about all we can say there. Can't really state whether it's greater than or less than. We can only state what we were testing for, and that was whether it did or did not equal 16.3. So if we would have done a right or a left-tailed test here, we might have set this up slightly different. Okay, so that will end this video.